All right, day 3, intro to polars. So let's back up before we even get to polar. Let's sort of talk about what you know and what you didn't know that you knew. Like, so far you've only been using the Cartesian coordinate system. You probably didn't even know that that's what it was called. Also known as the rectangular coordinate system to graph. We've graphed points and lines and curves all based on XY. So here's your little warm-up for today. Why don't you graph those 4 points, and then we'll see if we're all at the same. Right? It's so easy, it's dumb, right? Like, just go left or right on the X coordinate and up and down for the Y coordinate, and there's your points. That's the old way of doing things. Today we're going to look at another way to graph called the polar coordinate system, as opposed to the rectangular coordinate system. This might seem familiar to you, since it very much relates to the trig stuff that we've been doing. Points in polar form are r comma theta. And theta can be in degrees or radians. R is the radius, and theta is the angle. Zero, zero is called the pole instead of the origin. So those aren't exactly interchangeable. People would know exactly what you meant if you said the origin when you really meant the pole, because it's the point at the middle of the graph. We just call it the pole for polar graphs. So there's point A. Okay, graphing these. These are, you gotta kind of adjust your brain. Your brain is so used to doing X and Y that you do it automatically. But this is not X and Y. This is R and theta. And usually it's best to use theta first. So that means we'll rotate pi over 3. So I'm looking for point B. And the copies are so small or so bad you can't really read them, but that's fine. You know where pi over 3 is, I hope. So we go to pi over 3. I guess you can kind of read it. And then the radius is out 6, so we're going to go out 6 along pi over 3. So here's my pi over 3. 1, 2, 3, 4, 5, 6. So there's point B. Rotate pi over 3, go out 6. Point C. Rotate over to 5 pi over 6 and go out 4. 1. And that first circle is 1. That first circle is not 0. The middle is 0. The first circle is 1. So 1, 2, 3, 4. Point C. Point D. Rotate 5 pi over 4. So go all the way around to 5 pi over 4. If your eyes are bad like mine and you can't keep up, I'm going to lay that stick on 5 pi over 4 just so my eyes work better. And then I'm going to count 8 out along 5 pi over 4. 1, 2, 3, 4, 5, 6, 7, 8. So there's point D. Alright, you try E and F. So rotate around and then go out however many you're supposed to. Alright, there's E and F. Any questions on those? So I guess the important thing, or at least the easier way for me to do it, is to rotate first and then use the radius. You can do it the other way, but to me it makes more sense to use the angle first. Alright, well, all of those had a positive R and a positive angle. So those were kind of the straightforward version. But theta can be negative as well. If theta is negative, we move in the clockwise direction. Right, just like we did previously. If it's a negative angle, we rotate what we think of as sort of backwards at this point. So I'm going to rotate backwards pi over 3. So backwards pi over 3 would put me right there. Now, I hope most of you are familiar enough and can just sort of figure them out. But if you don't like going negative angles, do you remember what you could do that would get you the same landing spot, coterminal? You could add or subtract 2 pi. Now, subtracting 2 pi would only make it more negative, so I wouldn't do that. But if you don't like the negative angles, you can always add 2 pi. So, or maybe maybe pi over 3 is easy to go backwards, but when you get to something crazier, you're like, I think I want to add 2 pi to that. So if you add 2 pi to negative pi over 3, you'd get 5 pi over 3. So if you need to do it that way, that's fine. Rotate around positively to 5 pi over 3, or rotate backwards pi over 3, and then go out 6. 1, 2, 3, 4, 5, 6. Point G. Point H, go backwards 5 pi over 6. So that's almost pi around, so go almost 1, or almost to pi, halfway. Or if you don't like that, you add 12 over 6 and you get 7 pi over 6. So again, you can always avoid the negative angles if you like. 5 pi over 6, or negative 5 pi over 6 and out 4. 1, 2, 3, 4. How about negative 5 pi over 4? What quadrant would that land you in? Let's get that way. That would be the second quadrant. Toby, did you add 2 pi, or did you just sort of know where it landed?
I just kind of...
And that's fine. That's better if you just kind of can figure it out. If you need to add 2 pi, that takes a little bit longer. It's a little more mechanical, but maybe it's safer if you need it. But yeah, that's in the second quadrant at the over 4 marker. And then we'll go out 8. Again, I got my little helper here to keep my eyes online. 1, 2, 3, 4, 5, 6, 7, 8. There's J. All right, you try K, L, and M. So there's the points K, L, M. This question, what do you notice about the point 90? I'm not sure what you're supposed to notice about the point 90, except that if you read the next question, what would the rectangular coordinates of this point be? The others are all kind of weird, but this point you should be able to figure out. In XY form, how would you describe this point?
1, 0.
Well, how far out did we go? And how far up did we go? So that's kind of on there, like that's a fluky thing that only happens when you're on the x-axis, that the polar point and the rectangular point are the same numbers. I wouldn't even say they're the same because they don't mean the same thing. This one's r and theta, this one's x and y. They just happen to be the same numbers. And it only happens when y is 0. So I don't know. It doesn't matter. It's just kind of interesting. They're both 90. The 9 and the 0 represent different things, but you land at the same spot. All right, well, that was negative angles. Turn the page, and just as theta can be negative, r can be negative as well. Any guesses on what you do with a negative r? I bet you guessed correctly. Go the opposite way. So this is where a little helper stick ruler I think is helpful. So I'm still going to do theta first. So I'm going to go over to pi over 3. But instead of going out 6 along pi over 3, I'm going to go backwards. Backwards, sort of along the same angle. So this is where I think a ruler or a popsicle stick or a pencil or an ID or something is helpful. Because if you don't, a lot of times when people go backwards, somehow when they back up, their angle shifts. Like, I know what they're trying, but they've shifted one way or the other. All right, so here's pi over 3, but I want to go backwards 6. 1, 2, 3, 4, 5, 6. So point in. By the way, how else could you describe point in before we start graphing others? If you didn't want to use the negative 6, if you wanted to use a positive 6, what angle would you use? What angle is it sitting on right now? It's hard to read, but it's sitting on 4 pi over 3. Let's graph P. So we'll go to 5 pi over 6. Again, maybe your eyes are better than mine and you can go across and stay on line. But again, I think a straight edge is helpful. So instead of going out 4, we're going to go back 4. 1, 2, 3, 4. So there's point P. Pick on somebody now. So if I wanted to describe point P, Cecilia, with a positive R, what angle would I use?
11 pi over 6.
Good. All right, point Q, go around to 5 pi over 4, which is right here, but then we want to go backwards 8. Remember, so on these graphs, I know the last one is 9, so I can kind of cheat. Instead of counting all the way out there, I'm just going to back up 1 from the outermost spot. That's point 8 out there, or the 8, radius 8. All right, if I wanted to describe Q with a positive R, it would be 8. But Austin, what would the radius, or not the radius is 8. What angle would you say? Pi over 4. Let's see. It's like, how many more of these do we need to do, I guess? Why don't you do R, S, and T? Try R, S, and T. So there's R, S, and T. Okay with those? The backwards ones, the double negative thing is what will get some people. You just got to be slow, be careful. Again, use the helper stick if you need it, or an ID. All right, we've sort of mentioned this, but since theta can be positive or negative, and theta can be more than 2 pi or less than negative 2 pi, and r can be positive or negative, we can name the same point in a lot of ways. You know how many different ways you could name any of those points? Infinite, because you could spin around as many times as you wanted to. So you could add 2 pi times 100 to any of these numbers and get the same point. So this is very different. This little characteristic is very different than rectangular, right? In rectangular, there's only one way to get to 2, 3. Or there's only one name for the point 2, 3. 2, 3. There's no other way to get there. But in polar, you can spin around, you can go backwards. There's just a lot of different ways you can get there. So number 4, name the point 3 comma pi over 3 in 3 more ways. Well, I think it would probably be helpful to graph that. So pi over 3, and then go out 3. So somewhere about right there. So one way I could name it is if we just went backwards. Like, I still want to keep the 3, but how far backwards would I need to go? What would the negative angle be? How far backwards is that angle? 5 pi over 3. Because it's 6 pi over 3 all the way around. So negative 5 pi over 3 would land me at the same spot. Now, if I wanted to get tricky and use a negative 3, well, that means I would need to land on the opposite side so that the negative would send me back into the first quadrant. This is kind of weird. So if this angle is pi over 3, what is this angle? 4 pi over 3, because it's pi away. So I could go to 4 pi over 3, but then go back 3. Let's see. I could do negative, negative. So I would need to go backwards to this spot and then backwards 3. So backwards 3 is easy. But if this is 4 pi over 3, how far is the backwards angle? Negative 2 pi over 3. So this is kind of weird. There's 4 different ways to name that one point. I mean, there is 4 different ways. There are infinitely more ways to name that point. In fact, you could add 2 pi to any of those angles, and you'd have another way to name the point. Number 5 is sort of asking it the opposite way. Which of the following is not the same as 4 comma 2 pi over 3? And again, I think a little picture is helpful. So there's 4 comma 2 pi over 3. All right, why don't you see if you can figure out which one of those is not the same thing? How do we go back and forth between a polar form, r theta, and a rectangular form, xy? Thank you. So, draw a picture of any point. There's our point. And that point is r theta, and that point is xy. Right? There's 2 ways to describe it. The xy way is the way we're familiar with, x and y. The r theta way is the way we just learned. But there's some sort of relationship between all of those. In fact, let's see. X in terms of r and theta. So x, r, and theta, let's see. That looks like adjacent and hypotenuse relative to theta. So what trig function goes with adjacent and hypotenuse? So cosine of theta equals x over r. And if we multiply the r over, we get x equals r cosine theta. Again, this is like the 14th time, maybe not quite 14, but like every time x and y and sine and cosine show up, cosine goes with x, sine goes with y. That continues today. y in terms of r and theta. So theta, r, and y, that looks like opposite in hypotenuse. Sine of theta equals y over r. And multiply by r, we get r sine theta. Theta in terms of x and y. So what trig function here if we have y and x? Tangent. Tangent of theta equals opposite over hypotenuse. Y over x. How about an equation with, probably should have started with this one because I think this is the easiest one. Like an equation with x and y and r. So forget theta, just how are x, y, and r related? If that's a right triangle right there.
Oh, x squared plus y squared plus
Yes. Which means, I don't know if this is really important to write this down, but r is the square root of x squared plus y squared. Alright, so you turn the page and you see we have those equations all boxed because they are important. Starred, you need to know them. We won't give them to you. But they're not hard to come up with. If you just draw any old point you like and call it x, y, and r theta and then label everybody, like all of those equations, all of those equations come from that picture. So, do you need to memorize them? I don't know. That's why it says know there rather than memorize. Like, you definitely need to understand those. If you need to memorize them, memorize them. Hopefully you can sort of figure them out. All right, write the polar point. So that's an r theta in rectangular form. Some people can do this, rectangular form meaning xy. Some people can do this without a picture. I guess this is like all math problems. A few people can handle it without the picture. Most of us mortals like to see a picture. So pi over 4 and then go out 3. So there's a picture of the point. 'Cause to me, if I draw a picture of the point, then I can come up with x and y without really thinking about equations. But if you're thinking equations, x equals r cosine theta. So 3 cosine pi over 4 cosine of pi over 4. Oh, I don't have to think about that because I can call on Noah to think about that for me. Noah, what's the cosine of pi over 4?
That would be square root of 2 over 2.
There you go. Got a little excited there. Square root of 2 over 2. So 3 root 2 over 2. Y is equal to r sine theta. So 3 sine pi over 4. Danny, what's the sine of pi over 4? Square root of 2 over 2. So 3 root 2 over 2. Oops, over 2. So now I've got my x coordinate and my y coordinate. Oops. 3 root 2, comma 3 root 2 over 2. Both of them over 2. Again, is the picture helpful? It is to me, but if you just want to jump to the equations, you can do it that way. 6 cosine 5 pi over 3. Y equals 6 sine 5 pi over 3. Although I just can't help myself. I got to draw a picture. Plus the picture helps me with sines and cosines while I'm there. Austin, what's the cosine of 5 pi over 3?
1/2.
Good. Evan, how about the sine of 5 pi over 3?
Would that be 1/2? Oh wait, 1/2?
The sine is the long side right there. Another advantage of drawing the picture. Definitely negative, but the short side was 1/2, so the long side,
Negative square root of 3 over 2.
there we go. So my coordinates then is 3 comma negative 3 root 3. So you can just follow the pattern and not even worry about the picture. I still think the picture's helpful. Let's see, 3 pi over 2 comma 7. Occasionally you hit one like that and you might not even worry about formulas. If your point is straight down, Landry, can you tell me the coordinates of that point? That distance is 7 without even doing x and y stuff? I want that point in xy though.
Then 0, 1. Sorry,
Negative, how far down did we go?
7.
0, negative 7. So if it lands on a quadrant, sometimes you can figure it out without doing the cosines and sines. Most of the time you're not going to recognize that. You're going to be in the zone of just writing the equation. 7 cosine 3 pi over 2. But what's the cosine of 3 pi over 2? 0. Y equals 7 sine 3 pi over 2. Sine of 3 pi over 2 is negative 1. So negative 7. So the formula still works, but occasionally, and by occasionally I mean only if it lands on the axes, you can get it without using the equations. Let's jump to the next set here. When converting from rectangular to polar, so we're going the other way now. We're given x and y, and we want to change it into r theta. Please be careful with theta because there's quadrant issues that come up. As long as you'll graph it, you'll probably be fine. So the solution is to graph the point, and then you'll know what quadrant you're in, and you'll get the angle correct, most likely. So let's graph negative 1 comma root 3. So negative 1 root 3. Which one of those numbers is bigger? 1 or root 3? Root 3. So it helps if you can graph it reasonably to scale. Negative 1 root 3, because then I discover that is the steep angle in the second quadrant. So I've got x squared plus y squared equals r squared. So 1 plus 3, though, that was kind of nice. So r is 2. Tangent of theta is opposite over adjacent, or y over x. So tangent is equal to negative root 3. So what angle has a tangent of negative square root of 3? The old tangent 3 trick still needed. It's definitely over 3. And we just drew a picture of it in the second quadrant, so it's got to be 2 pi over 3. The trick is, if you don't have the picture and you just get to tangent equals negative square root of 3, you might answer that the angle is negative pi over 3. And that's sort of right based on this equation, but my picture is in the second quadrant, so I've got to use the second quadrant angle. So be careful on the quadrant. But if you draw the picture, it's hard to go wrong. Number 11, write the rectangular point 3 comma negative root 3. And again, if you'll draw it reasonably to scale, things go well. Which one of those numbers is bigger, 3 or square root of 3? 3. So I'll go out a long way and then down a little bit. And it doesn't have to be perfectly to scale, but it's helpful if you get the long and short pieces right. Why don't you finish that one? See if you can find r and theta. Yeah, it completely doesn't matter. Luke answered first, so we'll go with 11 pi over 6. But if you looked at that and saw negative pi over 6, that's completely okay, because there's more than one way to name a point in polar form. Not in rectangular form, but in polar form. All right, try number 12. I'm not going to do anything on number 12. You try number 12. Does anybody know what I'm about to do here? Complete the square. So half of b is negative 1. Half it, square it, add it is the key part of completing the square. Square it, we get positive 1, and then add it to both sides. So x minus 1 squared plus y squared equals 1. So that's a circle with center. Remember this all the way back to last semester? Where's the center of that circle? 1, 0. And its radius is 1. Be careful, because that's r squared over there. So there's our equation, but if we wanted to graph it, we need to change it into that, and then we could graph it. All right, a lot of stuff covered today, but it's block day, and you still have plenty of time to work on the worksheet, worksheet number 3. So again, we shifted from parametric, that was the key stuff. Now we're into polar, which is the R stuff. By the way, you don't get a calculator for this, but if you did, and you went to mode, we're learning all about your calculator. Look at function, that's what you used to. Parametric we just did, but the next one over is polar. And if you go to y equals on polar, you don't get y equals, you get r equals. And just to convince ourselves we did this one right, 2 cosine theta we think is a circle. Where did it go? Probably because it's too small right now. I don't know why that's not working. Radius of 1. Huh. I don't know why that's not drawing me a circle. Something's messed up. Oh well. That's why we're not playing with calculators today.